is all about basic pump and motor theory. As I said earlier, my name is Hafi and I am a product specialist in Grundfos. I will be talking about pumps and the motors only, and I will take from a very basic minimum. So we will start with the very basic of what actually is a pump. So this will be our very first topic, that what exactly is pump, what it do, what are the components will be our second topic. So what are the components which make up a pump, and what are the functionalities of those components. Then we'll talk about the types of the pumps. So how many types we have for the pumps, and why we have so many types. I mean, why we don't have only one pump and just stick with it. No, there is a reason that we have a lot of many types of the pumps. Then we'll talk about pump performance, how they are performing, how we can adjust the performance, because pump is a machine and we can adjust the performance of the machine. So how we can do that, there are several ways, we are going to talk about that. Then in pumps there is something called cavitation, or you can say the pump killer, so which kills the pump or which eats the pump away. We'll talk about the cavitation, how it happens, what is the cavitation, and how we can avoid the cavitation. So this part here will all cover about the pump. The next part of our session will be about the motors. Now motors are very basic machine of today's era. It is used everywhere. It is used with the pump for sure, it is used with the fans, it is used in ACs, it is used everywhere in our domestic or industrial life. So what we are going to talk about today will be squirrel cage induction motor, which is almost the 80% of the market of motors. And we'll talk about the motor basics, the torque and the power, which is exactly the output of the motor. What exactly is the output? The standards of the AC motors. So what standards are applicable for those motors, which we are going to talk about, and how we can get a same motor even we are buying for a different manufacturer, or we are even buying from different countries, we eventually get somewhat very similar motors. And what are the two major standards? One is American and one is International Electrotechnical Standards, IEC. So we'll talk about IEC in detail. Then we'll talk about motor protections, how we can protect the motor, because motor is a machine and it will work for day in day out, 24 hours a day and 7 days a week. So how we can protect the motor so that we can have as long life of the motor as possible. And what are the standard starting methods of the pump, so how we can start the motor. So this is today's agenda. Overall we will be covering many things in the pumps. I hope it will be useful for everyone. As I said in the very beginning of the presentation today, if you have any question, just keep writing your questions in the chat. So once I will finish the pumps portion or pumps module, I will open the chat and answer all the questions related to the pump. And after, once we will finish the motor module, we will open all the questions related to the motor and answer all of them one by one. I hope this will help all of us. So starting from the pump, what actually is the pump? The pump is a machine which gives flow and the head. So what is the meaning of flow? Flow is the amount of water moving from one point to another. So it is denoted by meter cube, is the amount of the water, and how much meter cube is moved in 1 hour. So this is the flow rate. The head is the distance, how far the pump is able to deliver the water. So these are the two, you can say, outcomes of the pump. This is what the pump delivers. Now, to make it more understanding, let's consider this. This is our schematic. We have this pump here. This pump, what it is doing is filling a swimming pool of 10 meter cube. 10 meter cubes mean that this swimming pool have a capacity of holding 10 10,000 liters of water. So 10 meter cube is actually is 10,000 liters. And then we have a source means this is the place from where the water is taken into the pump, and it is going all the way to this swimming pool. Now what I usually say, that if we have a pump, we can cover up a distance. For example, this pump was installed in the basement, and the water which is it is taking from an underground tank, the water will not go against the gravity to fill the swimming pool. So what we have to do is we need a device which can push all the water, which is 10,000 liters or 10 meter cube, inside the swimming pool so that it can be filled. So what machine we will use for that purpose is a pump. So what the pump is giving here, two things. One is the flow rate. The flow rate means how much amount of water is delivered in 1 hour, and one is the head, the pressure, how much distance this water is covering. This distance could be vertical, which is this distance from here to here. This could be a vertical distance, or this could be a horizontal distance plus the friction losses, because there will be some frictional losses also. So to combine all of them, the pump will provide some amount of flow at some pressure. So let's understand what is the amount of flow. Let's say I take a pump of 1 meter cube per hour. What it is saying, this pump will take 1000 liters and push this 1000 liter to the swimming pool in 1 hour. That's very good. Okay, then how long this swimming pool will take to fill for 10 cubic meter? So it will take, very simple, 10 hours. So it will take 10 hours. But for example, you want to have to fill the swimming pool faster. So what you will do, you will not take the pump with 1 meter cube per hour. You will take a pump with 5 meter cube per hour. So what does this say? This says that this parameter, meter cube per hour, is actually the size of the pump, how fast this pump can fill this swimming pool of 1000 liters. Now if I take a pump of 5 meter cube per hour, earlier it was taking 10 hours, now it will just take 2 hours to fill the complete tank. This is very good, very nice. I mean, I can do the job in less than 2 hours. I can fill the swimming pool. Now for example, you come to a point where you want to have a pump which can fill the swimming pool in just 1 hour. So you need the pump of 10 meter cube per hour, and then this swimming pool will be filled in just 1 hour. So what is the meaning? How we can select it? At the end of the day, it depends on the designer, or it depends on the owner, that how big he wants his machine to be to fill this swimming pool, or how fast he wants this swimming pool to be filled. For example, you are a homeowner and you have this swimming pool, and 10 meter cube pump per hour pump is costing, for example, $200, but 1 cubic meter is costing you $100. So you will make a decision. Is it okay for you to fill the swimming pool in 10 hours? Then $100 is also okay. But if your requirement is very strict, that you have to fill the swimming pool in less than 1 hour, then you have to go with this. So this is the sizing. This is the size of the pump. This is how the pump or the hydraulic machine works, that it gives you a certain amount of water at a certain distance. Now consider this head. This swimming pool was just above the pump, so this head would be not more than 5 meters. So this pump was just giving only 5 meters of the pressure. But for example, this swimming pool is at a distance of 30 meters and at the height of around, for example, 15 meters. So this is 15 meters high and 30 meters long. So the total head would be around approximately you will need not 45, because this is friction, so I would say around 20 meter of the pressure you will need out of the pump, so that the water which you are pushing from here will eventually reach to this point. So this is the two very basic components of the pump. This is what is pump is made or designed for, to give you what? First, the flow, the amount of water. The second, to some distance. Now, moving forward, the pump was first designed in 1689 by a physicist, Denis Papin. This is the most used tool among the around the world for moving the liquid. So whenever you have this movement of water, you will use some kind of a pump. Now, what are the components of the pump? Because pump is a machine. It must have made with some sort of a component. So what are those components? So the first of the component is volute. It is a volute, bearing, impeller, shaft, compression ring, and bearings. I know for some of you these terms will look like out of the world, because it might be very new for you, or for some of you, you might already know. So to make things simpler, I have a small animation. This is how the pumps look, and this is the volute. This is the moving part, is the impeller. This is the shaft of the pump. These are the bearings. This is the packing gland. This is the inlet, and this is the outlet of the pump. So from here you can easily see this volute. The water is coming inside from this side. This pump is rotating and throwing the water outside. Very simple. Nothing very complicated about it. But the thing which is complicated is how to select the right pump, or how to select the right pump with the longest possible life, or what are the components, when to use stainless steel material in this impeller, when to use stainless steel volute, or when to use gland packing, or when to use mechanical shaft seal, what are these bearing for. So all of these questions we will be discussing in coming some slides. So first we'll start with volute casing. Now, what is volute casing? Volute casing is this shell-like a part, the housing of the pump, which is responsible for receiving the water. So the pipe which will come will connect to this part of the pump, and then to connect the pipe of the discharge. So the discharge pipe will be connected to this port. So this is the suction port, and this is the discharge port. So this round shape is called the volute, or the casing of the pump. Now, there are two types of the volute: single volute casing and double volute casing. In single volute casing, if you will see here, that there is no vein, or there is no partition in between. Usually this is used in smaller pumps, or in majority of the industrial pumps. But whenever the flow goes above a higher range, we use some small vein or a diffuser in between. What this do, it reduces, or it channelizes the radial forces on the impeller, because once the water is pushing, this force is pushing here, or you can otherwise say this force is pushing here. So all the water which the pump is pushing, the impeller is pushing against this wall. So by adding this additional vein, or additional wall, or additional partition in between, we divide the flow going out. So earlier the total flow was going out from here. I can say the total flow is going out from here. In this one here, this is flow 1 and this is flow 2. So this is the total flow which is going out. Now there are two flows divided into two parts. How this will help? This will help to divide the radial forces to the pump. Earlier the total flow was giving the radial forces to the pump. Now this force is different than this force, and then this will not make any additional forces to the impeller. So all the forces in between will be taken care by this additional partition in between. So this will help to increase the life of the pump by reducing the radial forces. What are the radial forces? These forces on the impeller and on the shaft and on the bearings, because I show you there are a lot of components connected to this impeller. All of the life of these components will increase to have this vane. Now sometimes there is an additional diffuser. Stationary diffusers are used, like this, like this, like this, or this, or this, or this. The purpose of these diffusers are also the same: to reduce the radial forces on the impeller, to divide the flow into the smaller chunks, so that all the forces which are acting on the shaft of the impeller is reduced. Now, going back to our animation, this is my impeller. Okay, well, this is my volute. The impeller is rotating inside. This is the suction. Once the water will come inside, it will go inside the eye of the impeller. From here it will rotate. This is the part which will push the water towards the outside. So this will be rotating at a very high speed, thus high speed of 3650 rotation per minute usually. So when the pump will be rotating at a very high speed, the pressure will be generated. And this particular pump which I'm trying to show you here have no vane inside it. So the pump will directly push the water outside, and all the radial forces will be acting on this shaft. And once the radial forces will be acting, it will also affect the life of the bearing, this bearing, and the mechanical seal. So all of these components have some rated radial forces acceptance, so they can accept up to a certain level. That's why the smaller range of such pumps will come without any vane, or this we can say this is a pump without a partition, or no double volute is given. But when the flow will increase, you will usually find a small partition between the discharge of the pump. And even if the flow increase further, some of the pumps are even having a partition in the suction as well. Why? To reduce the axial forces which will come and hit the impeller into two. So this is another type of the pump. So there are many different designs of these volutes and casing, depending on the flow you have, depending on the application you have, and so on and so forth. So this was all about the volute. The next one is veering. Now what is a veering? Veering is a small circular ring which is installed exactly at this point. This is a veering. If you can see here, there's an additional ring here. What does this ring do? This ring makes sure that no water from this high pressure zone, because all the water in this zone will be with high pressure compared to this zone, because this is the suction. You are taking the water inside from a low pressure point, and then the impeller is rotating and increasing the pressure. So where the pressure is increasing? In this zone. This veering makes sure that no water is leaking back to the suction, because the phenomena of physics is that every time the flow of water will be from high pressure to low pressure. So we don't want water to go back to the suction, because the suction pressure is not as high as the discharge or the volute pressure. So this veering is used to have no clearance or minimum bare clearance possible in the rotating part of the impeller and the volute. So no water can leak back through the suction into the suction line. So as from the name, you can also imagine that this is a veering. Veering means that it will wear out with the passage of time, or you can say it will damage with the passage, or it will consume, just like a brake pad of a car. You need to change the brake pad of a car after some time. So how you can do that? You can do that by just opening the tire, removing the brake pads, installing a new one. The same case goes with the pump. Once it have some where you need to change the bearing, you will just open the assembly, remove the impeller, remove the shaft, change the bearing. It is a consumable part. So this was the second component. I hope things are going well. If you have any questions, just feel free to drop here. I just wanted to check everything is okay. So coming back to the next component, the most important component of the pump is the impeller. The impeller is this rotating part which rotates sometimes at a very high speed. So this rotating part is the part which will actually generate the pressure, or which will actually push the water outside this nozzle or the discharge port. In standard term, it's called discharge port. So this impeller is made of is made of different materials. This could be stainless steel, bronze, cast iron, titanium sometime when the application is seawater, and sometime it have a lot of different coatings. But what is the impeller? So impeller is the moving part or the moving component inside the volute which will generate the pressure. There are three types of impellers. The first one is open impeller. The open impeller is the one which do not have this any disc around its vanes. So this part, this small part which you see here, this small part which is moving around the curve part is the vane of the impeller. If you can see from inside, you can able to see from here also that, these are the vanes of the impeller. Vanes of the impellers mean that these are the components, or these are the design is such a way that this will be pushing the water. So there are three types of impellers. The first one, there is no disc around the impeller. So this is the impeller, no disc on this side, no disc on that side. This is called open impeller. Semi-open impeller is the impeller which have a disc on one side, but the other side is completely open. So this is semi-open impeller. The third impeller and the most used impeller is the closed impeller. The closed impeller have a disc on both sides of the vanes. And this impeller is a very good example, or not a good example, this is a closed impeller. Why? Because you have this disc on one side of the impeller or the vane, and this disc on the other side of the vane. So this impeller is a closed impeller. The eye of the impeller is the place from where the water will come in. So this is the place from where the water will come in. Once the water will come in, it will push through these veins. Once it is pushed, it will come out of this nozzle. So this is how the operation of the impeller works. So from here the water comes in, pushed by these impellers, and from here the water goes pushed out. Very simple. So this is the two major components of the pump: the volute, the casing, and the impeller. Now coming to the third most important part of the pump is the shaft. The shaft of the pump is the component which runs throughout the pump and connect the pump to the driving force. The driving force could be an electric motor, could be a steam engine or diesel engine, or could be anything which can rotate something, or which you can say, if it is light enough, you can rotate by your own hand, but it will not be very simple because it will require a lot of energy. So usually it is electric motor or diesel engine. These are the two primary source of movers which are connected to this end of the pump, which is called the drive end. Now this shaft runs throughout the pump. You can see the two bearings are there. You can see a shaft seal is there, and the impeller is mounted on the shaft. So the shaft is the rod of a metal which goes through the pump and helps to rotate the impeller. And this is the connection between the rotating part, or the rotating machine, which motor, which we will discuss in the next part of this training, and the impeller, which is generating the pressure. Shafts can come in different materials. Usually the shafts are in stainless steel, but it is available in different material. It depends on the application. In some application we need more stiffness or hardness, because sometimes the initial torque is very high. We don't want that the motor is trying to twist this shaft, but because of the very high load in the impeller, the shaft itself is twisted. So the shaft is the hardest possible part inside the pump. So this is shaft. Now something which is very important, which is compression packing or mechanical seal. Now why we need this? This is the very first question. Why we actually need a compression packing or you can say a mechanical seal? The reason to have is very similar to have a wear ring. Why? Because if you can see, the pressure in this part of the pump will be very high compared to the pressure in this part, or in the air. This is the air around here. This is the atmosphere. Because once you will be seeing the pump in your daily life, it will look something like this to you. This is how the pump will be looking to you, rotating, and this is the atmosphere you have. The pressure inside this volute is very high, whereas the pressure inside this volute is very high, and the pressure outside, the atmospheric pressure is relatively very low. So there is a chance that if we do not have any such device, a compression packing or mechanical seals, the water will come and push through out from here, because we need something which rotates, and to give the rotational possibility, we have to give the space for rotation. And if we give a space to rotation, that means there is a space for the water to come out as well, because what we have is exactly very high pressurized water in this part of the pump. So to avoid water coming back in the atmosphere, we use mechanical seals, or we can say shaft seals, or the gland packing, or compressional packing. All of these have the same work and same meaning. The major job of all of this is to do what? Is to do not to have water coming out from the very high volute pressure into the atmosphere. There are different types of it. There's compression packing, which is called gland packing. This is a very old technology. Not very old, a relatively older technology, which is used nowadays only in majority of the fire pumps. But nowadays, majority of the time, mechanical seals are used, and we will discuss them later in the course, what are the differences and which one is better and when to use which. But the major task of this shaft seal is to separate the liquid from the atmosphere. So we do not want any high pressure water coming out of this volute into or towards the shaft, or towards the motor, or towards the atmosphere. So this is the task of mechanical seal. Bearings. If you can see here, there are two bearings, this one and this one. It depends, usually it depends on the pump manufacturing or pump type. Some pumps have one bearing only, some pumps have two bearings, some pumps have ball bearings, some pumps have pin bearings. They are all different, but you must find one or two bearings, or even more than two bearings in any kind of the pump. The reason to have the bearing is to give non-frictional rotational possibility, and to absorb all possible radial load or radial force which will act on the impeller. So the shaft will be balanced between these two bearings. It will be always in line, and it will help to rotate this impeller with very or bare minimum possible friction possible in the pump. So these two bearings will be required and used for this purpose. Then types of, now this is this usually covers most of what is in the components. We covered the volute. This is the volute. We covered the impeller. We covered the shaft. We covered the bearings, the two bearings which will help. Usually they are ball bearings. Then we have the gland packing or compression packing or shaft seal here. One specific thing which is extra in this pump is this gland follower, or you can say this is a sort of an equipment which helps to tighten this gland packing, because once the pump is rotating for a very long period of time, like 1 year or 2 years, only gland packing, not the mechanical seal, the gland packing will be loose. To tight what will happen when it will loose? The water will start dripping out in a faster pace. So you will have a lot of water coming out, not a lot of drops of the water. Comparatively, the general standard is not to have more than 2 or 3 drops per hour. But if you have loose packing, probably you will have a lot of water or a lot of drops of water coming out of the packing. So this follower screw will help. Once you have this situation, you can tighten it. It will push through it and it will tighten it back. So it will do to a certain space. If you can see here, we have this much space. Once all of this space is finished, you need to disassemble the pump and change this gland packing. So the next topic we will talk about is the shaft seal types. The sealing which will help not the water to go into the atmosphere. What are the types? There are 3 major types of stuffing of shaft seals. The first one is stuffing box. This is the one which we saw in this example, is stuffing box. The second one is lip seal. The third one is mechanical seal. Now in stuffing box, it is a braided stuffing box packing in the simplest type of the shaft seal. It is a very simple type of the shaft seal. In this one, this is your shaft. This is the housing of the pump. This is the 2 parts. This is your stuffing. So what will happen? This shaft will rotate. This shaft will create a rotation. And once it is rotating, it will rub through this part. So this part will be always rubbed. So the temperature over here will go high for sure. You have a chance of the leakage, or not the chance. You will always have a leakage in stuffing box or compression packing, because the pressure here will be very high. This is the high pressure, and this is the pressure of atmosphere, which is only 1 bars. So the pressure here is very low and the pressure here is very high. So what will happen? This water will try to sneak through here every time this is rotating. Once this gland packing will become loose, when this gland packing become loose, more water will go through it and goes to the atmosphere. What will happen? When more water will go to the atmosphere, first of all, your efficiency will go down. This is the first thing which will happen. The second thing, you will have a lot of water dropped around around the pump. That's why most of the time below this pump you will find a drip pan. A drip pan is a sort of a pan which is used to collect all the water which will eventually drop from here. So the drip pan is used to collect the water which will go out just because of rotation in the shaft caused this stuffing box to get loose. When this get loose, the higher pressure water comes out of it. One thing to see here is that it can the stuffing box can absorb some misalignment, although it will become very it will become damaged very quickly, but it can absorb some misalignment, but the wear and tear will be here. So vibration and misalignment will cause shaft seal to leak. The second one is a lip seal. Now in lip seal, there is no, you can say, there is no stuffing box. What you have is again a shaft seal which will rotate, and you have this housing. This is the housing, this is the clearance, but this clearance is stored because of this ring. This ring is pushing this towards this shaft seal, so the water do not have a space to go around. But if you can see these marks here, these marks are because of the friction caused between two two metals rubbing with each other. So this shaft is rubbing with this seal. So this is called lip seal. This is ideal in two situations. The first situation is low speed pumps and oil related pumps. So all the usually the oil related pump use this arrangement, lip seal arrangement. How we do the lubrication, because we do need to do the lubrication, otherwise if we don't do the lubrication, this will become very hot, and once it become very hot, there is a chance that it will deform. So the lubrication is done through the liquid which we are pumping, because the pressure of the liquid which we are pumping is high already. So this water will go and make a small film, very small thin film of water inside between this seal as well as this shaft. So what will happen if you don't have the water? This will damage very soon. So having no water is very disaster, or is a big disaster for a pump, because what you have to do, open the pump and change the shaft seal. Changing a shaft seal is again a wear part. So you need to change the shaft seal after some operation of the time, because this is rubbing against it. After some time, this will if you see, this groove will finish, and once this groove will finish, the water will start going out, so the shaft seal will leak. So the shaft seal is a wear part. Any pump in the world, you need to change the shaft seal, because shaft seal is just like a brake pad of your car. Again, coming back to the same example, because this is something which will consume throughout the operation of the pump. Now, the most commonly used shaft seal today is the mechanical shaft seal. What mechanical shaft seal is? Mechanical shaft seal, you have the same shaft which will rotate. The pump housing, this is the pump housing, which is the stationary part. This is the stationary part which will not rotate. This is the moving part. So in the shaft seal, you have two things. One is the stationary part, which will always be stationary. One is the rotational part, which will be rotating. And these two faces will always come in contact with each other and rub against each other. So these two faces are made of ceramic, a material which can withstand up to 150 or 200 degrees centigrade. And then you have this spring. This spring, what the spring is doing, this spring is pushing the moving part towards the stationary part. So what happens? Whenever the pump rotates, or even the pump is not rotating, this shaft seal is always mechanically pushing these two seal faces. This is called seal faces. These two seal faces against each other. Now the cooling is again done with the media or the liquid which we are pushing through the pump. So this will create a small a thin layer of water in between these seal faces, and this will provide a lubrication. Even with a very good lubrication and a very good operating temperature, with the passage of time, around 1 year, 2 year, depending on your installation, you need to change the shaft seal. But if in case you run the water in dry running condition is the condition in which there is no water. In such condition, you need to change the shaft seal in less than 1 hour, because the shaft seal will not sustain the very high temperature which will be generated between these rubbing faces. So never ever run the pump without the water, because the water which you are pushing is also the media for cooling the component such as the shaft seal of the pump. So this is the most important point you need to remember. Now coming to the types or different types of the pump and the characteristics. We can have the pump up to 100,000 meter cubes per hour, and the pressure up to 10,000, which is 10 kilometers, or up to 4, or not 10,000, this is up to 4,000. If you see here, I show radial flow pump, mixed flow pump, axial flow pump. These are three different kind of pumps. What happens? These are defined by the path of water which is taken inside the pump. For example, the water comes from here and leaves directly in the same direction it enters. That means that the impeller did not change the direction of the water. So what impeller did? Just push more water. This is called axial flow pumps. Axial flow pumps, the water is not changing the direction at any point. Whereas semi-axial, the water enters here, changed the direction, but went back to the same direction again. So it does change the direction, but not completely. So it is semi-axial impeller. The third one, the last one, is radial impeller. In this one, water comes in this direction but leaves at 90 degrees. So the angle between this and this is 90 degree, not C, 90 degrees. So the water comes at this point and leaves at this or either this point. So the water radially change the direction. This is called radial impellers. Now how this affect on the duty which this pump can give. If you can see here, radial pumps are good for high pressure. If you can see here, these are the pumps. Radial pumps can go up to 4,000 meter, but will be restricted to what? Around, sorry for this line, around you can say 1200 meter cube per hour. If you need very high pressure, go for radial impellers. If you need very high flow, then go for axial flow pumps. Then in between you will find single stage. I will talk about single stage and multi-stage in a while. You will find mixed flow pumps. You will find single stage for certain pressures, and if you need even more pressure, you have to go for even higher pressure, which is multi-stage radial pumps. So pumps can deliver very high flow and very high pressures. It usually depends on the application, which pumps will be used where. So one example of these pumps, this kind of pump are used in RO plants, because in RO plants we need the usual pressure we need is 40 bar. So can we get 40 bar with axial flow pumps? We are actually not getting possibly 10 bars with axial flow pumps. Axial flow pumps are not for pressure. Axial flow pumps are for flow. So in RO plants, we usually use radial impellers, but axial impellers are used in municipal water pumps or big wastewater pumps, or the pumps used to move the direction of the river. Sometimes the flow required is thousands of liters per second, but the head required is only 2 meter, 3 meter, 4 meter. So this kind of applications we use axial flow pumps or axial impellers. Now there is another difference in the type of the pump: single stage pump or multi-stage pump. In single stage pump, meaning we have only one impeller. This is the one impeller we have. We do not have more than one impeller. In multi-stage pump, we have more than one impeller. So in single stage pump, water comes from here, leaves from here, nothing more. In multi-stage pump, water comes from here, go from first stage to second stage to third stage to fourth stage, fifth stage, sixth stage, and usually it have an outgoing path from here and goes out from here. So what does it happen? How does it increases the pressure? Because in the last slide I said increasing the impellers or multi-stage pumps are used for higher pressure of the pump. This multi-stage pump is working as pumps connected in series, because the impeller, the water gets into the first impeller, leaves the first impeller with some pressure, enters the second impeller with some pressure, and then leaves the second impeller with the double pressure it enters. So as the impellers increases, the pressure generated by the pump is also increasing. So at the end you will have a very high pressure of the pump, and that is the reason nowadays we can find pumps which can go up to 100 bars very easily. So multi-stage pumps are used for high pressure applications, whereas single stage pumps are used for high flow applications, meaning the application in which we need more water to deliver. We don't need to deliver it to a very high distance. Or I will give you a very simple example. If you have a very big building, a very tall building like Kingdom Tower in Riyadh, if we want to install the pump in the basement of the Kingdom Tower to give the water to the topmost floor, you will use multi-stage pump, because if it is just one pump for one apartment in the topmost floor, you will have a very low flow, but you will need very high pressure. But if you want to irrigate very big land of irrigation, or if you want to irrigate very big land, your head required will be very low, because you just need to overcome the frictional losses. You don't need to overcome the geodetic, the height losses. So you will use single stage pumps. So this is where we use different pumps. Now we have something called closed couple pumps and long couple pumps. Closed couple pumps are the pumps which have this part inside, a coupling. So a coupling, what you will do with the help of coupling, you can remove this motor and and disassemble the motor and pump into two units. So you don't need to disassemble the pump if you need to do some maintenance on the motor, or vice versa. If you want to just remove the pump, you can remove the pump without removing the motor. And this is closed couple pump. Closed couple pump means that the shaft which extended from here, the shaft is extended from here, the impeller is also on the same shaft. So the motor shaft, which is starting from here, the motor shaft which is starting from here, and the pump shaft, they are both the same. So you do not have two shafts, or you might have stub shaft, but that's a different case. But closed couple, you do not have a space to decouple the pump and impeller, or pump and motor. So it is not possible. In long couple it is possible. So but this possibility comes with a small drawback. The drawback is you don't need to do the alignment in this. It is already aligned if it is connected. In this one, you need to do the alignment, making sure that the pump center line of the impeller shaft and the center line of the motor shaft is always in line. If they have even 1 degree of the change, you will reduce the life of the pump significantly. So alignment is something you need to do every time when you will disassemble the pump. So this is the only drawback. Coupling, as shown here, is used to couple, to join two different moving things together. The most common one coupling is this pin and the most common ones are pin and bush couplings are used, and many other kinds of couplings are used. They have different benefits, different drawbacks, but it do one and only one thing: to join the shaft of the motor to the shaft of the pump. So to join both of them, what you need to do is to use a coupling in between. So if you decouple the pump, the motor will be rotating, the pump will not rotate. So to make sure when the motor is rotating and the pump is rotating, you need to couple the pump. so which is done by this coupling. So based on all of these differences, in the world we have many kinds of different pumps. Some of them I shown here. There are many others of them which I am not showing here. Many other of them. I'm showing you the one which are mostly used in Saudi Arabia and in commercial buildings and industries. So some are end suction pumps. End suction pumps are the pumps where suction is from here and the discharge is from here. So it is 90 degrees to each other, and usually why we say it is end suction, because it is installed at the end of the line, because line will go up from there. The pipe line means the pipe, and suction, it is the suction is at the suction of the pump is the end of the line. Inline mean the water will come in this direction and go in the same direction. All of these pumps are inline. So what you can do to install the pump is very simple. You cut the pipe. For example, you need to install this inline pump here. So what you do, you cut the line from here, just install a pump, and there you have it. This is your pump. You don't need to change the structure of the piping to install the inline pumps. So usually these pumps are installed through a line, whereas this kind of pumps will be installed like this. So you will have a suction and the pump will go and it will go high. So now we have in end suction we have horizontal, we have single stage, multi-stage, meaning we have one stage or more than one stages. We have long coupled, close coupled. In inline we have horizontal, vertical, we have split case. Split case mean, if you see here, this part of the pump can be open and you can open this part. So if you need to change anything, wearing, shaft seal, bearing, anything, you don't need to decouple the pump or the motor. You just need to open the casing and do whatever you want to do here. You don't need to decouple the motor, the pump from the piping even. So this is the pump majority of the time is used with NWC or municipalities, because it is very easy to maintain or to change the wear parts, or the parts which will wear out very fast. Then we have in single stage we have long coupled pumps, horizontal, long coupled pumps, vertical, inline, and then we have close coupled pumps, and we have multi-stage close coupled pumps. So these are the close coupled multi-stage vertical inline pumps. Now this was all about the physical part, or how the pumps and how the pump and the motor and the things are rotating, or what are the components. Now in this part of the presentation, we'll talk about the pump curve. Pump curve is the documentation of the pump. How this pump will behave if it is running at a certain speed. What are the characteristics of the pump? You can say it is the data sheet. In the data sheet of the pump, this is the vital information you will find. And in this course, I will explain you how to read this curve and how to make your own curves. Now, in this pump curves, on the x-axis you will have flow. So increasing flow on the x-axis and increasing pressure on the y-axis. And then you have this pump curve. So what will happen, once you will increase the flow, the pressure developed by the pump will decrease. So more flow the pump will generate, less head the pump will generate. It is as simple as this. If I ask you to throw one glass of water, you will throw it further. But if I ask you to throw one complete jug or bucket of the water, you will not able to throw that big bucket of the water to the same distance, because the weight of the water increased. The same phenomena goes because the flow is inversely proportional to the head of the pump. So both are inversely proportional to each other. One will increase, the other will decrease. One will decrease, other will increase. Now in this pump curve, we can see at 70 meter cube per hour, this pump will generate approximately 41 meter of head. This is what we will call the duty point of the pump. meaning that the flow and head of the pump at the full speed. Maybe this pump is running at the full speed. So at full speed, if you run this pump, you will able to get 70 meter cube per hour and 41 meters of the pressure. Now, how to plot the efficiency of the curve? The efficiency of the curve is efficiency of the pump is the output power it is generating, which is denoted by this rho GQH. Rho is the density of the water which you are pushing. This is the constant 9.8. Flow is the flow which we are taking. In the last example, it will be 70 meter cube per hour. Head, from the last example, it will be 41 meters. If you combine all of them and take the density, which will be 1000, I think, based on the units. P2 is the power which this shaft is giving. So this shaft is giving some electric power, which we'll discuss in the second part of this course today. If you divide both of them, you will get the efficiency. Now, how you will plot, how the efficiency is plotted. This is the efficiency which is plotted. As the flow increases, your efficiency increases. At a certain point, you get your best efficiency. This point is called BEP, best efficiency point. That means that throughout the total flow of this pump, the efficiency was maximum at this point, which is around 65 or 60 to 70 meter cube per hour. That means that if you run the pump in this point, you will have the maximum life of the pump, the minimum bill which you will get out of the electricity, and the minimum wear and tear of the pump, because the vibration at this point is also minimum, because vibration is an enemy of the pump. Whenever you have a vibration, the life of the pump will go down. So having a minimum vibration at this point, meaning that your life of the pump will increase. So the BEP point is very, very important on your curve. So whenever you are purchasing or having a look on the pump curve, sometimes what people do, they say that the pump curve looks like this, it is very nice, just based on the looks. No, this is not right. What you have to always see, that where your best efficiency point is lying. For example, you selected a pump at this point. That means you selected a pump to operate at 40 meter cube per hour. Although it will operate, it will not create any problem. You will get 40 meter cube per hour. Your pump will not fail, but the total life of the pump will decrease, which is a big problem. You don't want to have a low life of the pump. Then the power consumption, how the pump will increase, how the power will be increased if the flow is increased. So once the flow start increasing, the power also start increasing. This point here is the maximum power this pump will take. So if I plot it here, this will be around something. But if I say I will be maximum working this pump on 70 meter cube per hour, that means that I will not go above 10 kilowatt, whereas the maximum power this pump can take is 11 kilowatt. So you need to make sure that the motor which is attached to this pump is bigger than this point. That is not always, but this is good to have. That means that your pump will never overload. But for example, you take 10 kilowatt motor with this pump. By default, the motor for this pump should be 12.5, or this is a good motor for this pump. But at 12 kilowatt, it will work, but you cannot go above 70 meter cube per hour. If you go above 70 meter cube per hour, your motor will start getting overloaded. So if you overload the motor for a long period of time, what will happen? Your motor will burn. So this is how you must need to you must need to have a look on your motor power consumption, or your power consumption of the pump, and match it with the motor attached to the pump. The maximum power of the pump which it can take at the full flow, the motor power should be bigger than that. The NPSH curve, we'll talk about cavitation in detail, but NPSH is the characteristic of the pump which says that what should be your minimum pressure, or minimum suction pressure, or minimum pressure at your section. So this is denoted by meters. As the flow increases, this minimum pressure increases. If you do not have this pressure, you are going to face cavitation. That means that your pump will get eroded, and you will have small dots on your impeller, and after some time your impeller will start getting eroded, so which is not good for your life or performance. So what we need to do, we need to make sure that at suction of our pump we always have pressure more than this. There are certain other parameters as well which we will discuss in the coming slides. Now this is the complete curve. We have till now we have seen all of these curves in separate ways. Now I combine all of them. If you see here, at 70 meter cube per hour, this is consuming the power, this is the NPSH, this is the head it will generate, this is the flow it will generate. Now if I say what will happen if you have this pump here and you have a throttling valve, you have a throttling valve and you close the valve a little bit, not 100%, a little bit, and your flow goes to 60 meter cube per hour. What will happen? Very simply, you just need to draw one line and then you will get all new parameters, which means that your new pressure will be this, which is 45. Earlier it was 41. The new pressure is 45. The new power consumed is 10 kilowatt. Earlier, is 9.5 kilowatt. Earlier it was 10 kilowatt. The new NPSH is 2. Earlier it was 3. So just by throttling one small valve after your pump, you are actually changing all the parameters of your pump. You are changing how much power it is consuming, you are changing how much NPSH it should have, you are changing how much head it is generating. So changing one throttling valve after your pump makes a lot of difference. For example, if you open it, earlier I was closing it. If I open it, I will go here. What happen if I go here? I will go here. What will happen if I go here? My flow will go to 80. My pressure will go to 35. My NPSH will go to very high, which is 5. My power consumption will go to 11. So I will increase all the parameters of the pump just by changing one throttling valve after the pump. So that's why it is very important to have the pump curve and to understand how it is operating. Now coming to the pump performance. We design the pumps, and I would say in Middle East, most of the pumps which are installed on the site are oversized. That's my personal impression, and it's my personal experience that we just try to increase a little bit, which is okay because we never know how the demand will change. We are ready for the future. This is very good. But is there any way to improve the pressure or to adjust the performance? Actually, there are 4 ways to adjust the performance of the pump. How we can do that? So the first one is by a throttling valve, which I just discussed in my previous slide. In this one, what we are actually doing is we are having a pump and we are having a throttling valve. Whenever we close the pump, we are going back on this curve. So what is happening? This was my earlier flow and this is my new flow if I'm closing. So if I'm closing, I'm going back. If I am opening, I'm going forward. So by throttling the valve after the pump, I can change the pressure which it is generating, meaning I can increase it, but at the expense of decreasing the flow. So I can increase the pressure, but I will decrease the flow. Or I can increase the flow, but I will decrease the pressure. So throttling is possible. For example, the example I will take in all of the all the processes or options of performance adjustment, I will decrease the flow. So decreasing the flow from 60 to 50 in first possible way in throttle control. So if I want to decrease the flow from 60 to 50, it is possible, and it will reduce the power from 100 to 94. So I will be reducing the power less. I will be using the power less. Earlier I was using 100%. Now I am reducing 6% less power. So this is first way. Just install a valve after the pump and you adjust the performance of the pump. The second way is installing a bypass valve. Now what bypass valve will do? Bypass valve, you will have a pump, you will have a T here. Now there is a law of T. Law of T mean this is actually a law of Kirchhoff's law, which is at any given point, if the current is coming, I1 coming in this point, I2 going in this point, and I3 going in this point, the sum I1 it will always be the sum of I2 plus I3. This is always the case. The same law is applicable here. If the flow Q1 is here and Q2 is here and Q2 is going in this direction, the sum of Q2 plus Q3 will always be equal to the flow which is coming out. But where the flow will go more? The place where the resistance is less. So over here this is R1, over here this is R2. If the R1 is less than R2, I2 will be greater than I3. In simple words of pumps, the resistance in hydraulic world is the resistance by this valve, by this throttling valve, which we are opening and closing. For example, if I open this valve 100%, it is completely open. What will happen? The flow will not go here, or very minimum amount of flow will go here. Most of the flow will go back to the pump and circulate inside the pump, which is not a very good idea. But let's say I just open it 10%. That means that too much friction is here. Some flow will go back, but majority of the flow will come here. So what I say, to improve, or in my previous example or my generic example, I'm going from 60 meter cube per hour to 50 meter cube per hour. To do that, I install a bypass flow and I open the bypass. So what happened? Some of the flow, or in this case 10 meter cube per hour, goes back and does not go to the system. So in system only 50 meter cube per hour go, but eventually I am consuming more power now. If I am consuming 100% earlier, now I am consuming 110%, because to give 50 meter cube per hour, 10 meter cube per hour is circulating inside the pump, this is a possibility to reduce the flow going into the system. You just open the bypass valve, but you will be consuming more power to do so. The third option to reduce the flow from 60 meter cube per hour to 50 meter cube per hour is to reduce the impeller size. So for example, earlier it was the diameter of the impeller was 200 millimeter. Now I do it let's say 150 millimeter. By this reduction, the surface area of the impeller, which was earlier pushing the water particles, is reduced, which means that the flow and the pressure generated of the pump both will reduce. So this is my example. I go from 60 to 50. From here I go from 70 to 55 meters. I reduce the pressure also. But if you can see here, if I was earlier taking 100 meter cube per hour, now I am taking 67 meter cube per hour, which is much less than which I was taking earlier. But this option or this solution have one small problem, which is if I trimmed it, I cannot go back. There is no going back. So once trimmed, you have to stick with this impeller, or otherwise you have to have one impeller of 200 millimeter, one impeller of 150 millimeter, one impeller of 100 millimeter. So whenever you don't have a demand, you open the pump, install 100 millimeter. Your demand increase, you stop the pump, open the pump, install 150 millimeter. And if your demand is at peak, you open the pump, install 200 millimeter. This is possible, but the workaround is very big, which creates a lot of hassle to change the impeller every time. So just few formulas how to determine the changes. The flow is directly proportional to the square of the change, which means that if you half the diameter, the flow will be reduced by 4 times. The head will be reduced also by 4 times, but the power will be reduced by 16 times. So the power reduction, if as we see here, was very high. So that's a good solution, but the workaround to always change the impeller is where we cannot go back. So if you have an application where the pump is designed to work only at one duty point, and you will not change the duty point, changing the diameter or using this solution of impeller trimming is good, because you don't need to change the duty point after that. You did it one time, that's it. But what if your demand is always changing? In that case, we will come to the last solution, which is speed control. In speed control, with the advancement of our new era of electronics, we have now devices which is connected to the pump, which is called VFDs, which are connected to the pump and which can change the speed of the pump from usually 20% to the 200% of the speed. So you can go as low as 20% of the pump speed and to the 100%, which means that you can change the load on the pump as many times as you want. Now, taking my same example earlier, I was going from 60 meter cube per hour to 50 meter cube per hour. What I do, I change my speed. Now I get from 70 meter head to 55 meter head, but the power consumed is 65% of the total power consumed earlier. That means I reduce the power consumed as well, while reducing the speed of the pump and going from 60 meter cube per hour to 50 meter cube per hour. Now, when you will actually need to do so, why you will need to go from 60 meter cube per hour to 50 meter cube per hour? For example, you are having a pump which is giving a water to one building, and that building, the water is going directly to all the taps. Now, in the night, everyone is sleeping. Will you still run the pump at 60 or 0? That means if no one is using, you will go to 0, and if 2% are using, you will run at 60. No, this VFD will help you to run even at you can say at this point 20 meter cube per hour. So this is also possible. So this is the reason, when your demand is changing, we need to change the performance of the pump as well. And how we can do that? These are the 4 ways which I discussed. We can change the performance, and the most, or I can say 80% of, or not 80, I can say 70% of the time, the speed control is used as the solution to reduce or to adjust the performance of the pump. Now, the same affinity law is applicable in this one, but with the different proportions. Now, if I reduce the speed to half, my flow will be half also. So this is directly proportional. My flow is directly proportional to my speed. If I reduce the flow in half, if I reduce the speed in half, my flow will be reduced to half also. But if I reduce the speed in half, my pressure will be reduced by the factor of 4, which is big reduction, and the power is even bigger reduction. If I reduce the power, or if I reduce the speed in half, my power will be reduced by 8 times, which is a big reduction and a big saving for us. That is the reason this concept of changing the speed is taking is used in majority of the places of the world, and is helping most of the people which have an application of variable demands, and they are varying the amount of the flow as well, or amount of the pressure or the speed. So this was affinity law and the performance adjustment. Now this small curve or a graph explains how your flow, pressure and power will change if you increase the speed. Now if I say my speed was 100, means my pump is working at one reference point. If I increase by 2, my flow will increase by 2, my head will increase by 4, my power will increase by 8. It should be going to 8, or not this point, actually this point. This should be going to 8. Now at this point you can anytime see that whenever, if this 2 is your maximum speed, whenever you go back, you always have a big saving in your system. Always have a big saving in your system. So this is the reason this concept of adjustment of the speed is very important in pumping networks. Now this is the summary. As we see, 94% was the power reduction in throttling. 110%, that means with bypass control, if you are using for reducing head and flow, you are actually increasing the power which is consumed. Impeller, we have the reduction of 67%, and speed control we have a reduction of 65%. Just this is an example of going from 60 meter cube per hour to 50 meter cube per hour. If you go even further, the reductions will be even higher. So I hope it was understanding. Now coming to the last point of today's pump basic course. This topic is about cavitation and NPSH. This usually is known as pump killer, because if a cavitation is happening in your pump, you will hear a very loud cracking noise. Cracking noise is like you will hear that you might not be pumping water, you are pumping stones. So you will hear very loud sounds of cracking inside your pump. You will feel a lot of vibration inside your pump. And what will happen? The result of this erosion, your impeller will be big time damaged because of this cavitation. And secondly, reduced performance. Your pump performance will be reduced drastically. How drastically? You remember, this is how the pump curve looks like, but after cavitation your pump curve will look something like this, or even worse than this. So cavitation is a major concern in pumping networks or in pumping systems. We'll talk about what is cavitation, how it is happening, and how we can stop them. So first of all, what is cavitation? Cavitation is explosion or implosion of small bubbles which are coming inside the water and hitting the impeller vanes. So you have a pump. I will open this thing again. Now you can see this is my impeller, and my impeller, all the water is coming inside. Now if the impeller is anyways rotating at a very high speed, now if the water is coming, and water is coming also with small bubbles inside them, those bubbles will come and hit and implode at the impeller. Once it will be imploded, it will take out with it some small portion of the impeller, some material of the impeller. what will happen with that? With one bubble, okay, it is a very small amount. But with many bubbles, that means if you have too many bubbles in your water, what will happen? You will not have these veins very soon. This vein or eye of the impeller will be damaged very fastly. These veins will be damaged very fastly because of the cavitation. Why this is happening? Because this small water bubbles which are coming through your suction is hitting and imploding on your back side of impeller. If you can see here, all of them are imploding on this side of your impeller. But the question here is from where these bubbles are coming. Now, if you can see here, pumps are designed to push the water. If only water is there and there is no bubbles, you will not have a cavitation. Cavitation is always happening because of the bubbles. But the question is from where the bubbles are coming. The bubbles are coming because sometimes the pressure, the P1 pressure at the suction drops below the vapor pressure of the water, which means that vapor pressure is the pressure. After that pressure, water start becoming the gas or start having the bubbles in it. For example, what is happening? You take a pot of water and pour some water. Take a pot of water and pour some water inside it, and you start boiling it. The first thing what will happen? You will have one small amount of bubbles, very small bubbles first in them, and then you will have a lot of bubbles when it is boiling above 100 degrees centigrade. But the same phenomena can also happen once the pressure at this side, the back side of your impeller, this side of your impeller drops below vapor pressure. Now how whenever the pressure at the suction will go below this line of water or the media which you are pumping, whenever the pressure will go below this, you will start having bubbles. Whenever you will have these bubbles, you will have cavitation. But the question is, why you have these bubbles? The pressure goes down. But why the pressure goes down? The pressure goes down because of several reasons.
Here we are.
I will share these videos with you. You can see them later on. Why this pressure goes below? The pressure goes below because the velocity of the water increased very high at the suction. That means that at this suction of the pump, the water which was coming inside the pump was at a very high velocity that it reduced the pressure. This is called Bernoulli's equation. So what happens is if the velocity increase, the pressure drops. So when the pressure drops and the pressure drops even further, that it goes below this vapor pressure, what will happen? You will have cavitation. So what we need to do, we need to avoid the very high velocity of the water, or we need to make sure that enough pressure is available at the suction part of the pump. So how we can make sure that enough pressure is available at the suction part? The first thing we can make sure is this very small calculation. This is called risk calculation of the pump cavitation. The first one, this over here, you can see this is the pump installed. This is the height of the pump which the pump will be sucking the water through. This is the barometric pressure. The pressure which is developed on this water surface by the atmosphere. So this pressure will be by atmosphere. This is HB. This is the frictional losses. As the water will be traveling through this pipe, you will always have some frictional losses in this pipe. And this is the pump. So NPSH, and again NPSH is also, we will have some NPSH requirement. You remember in the beginning of this course we talked about the NPSH requirement of the pump. This is some meters of the pressure which is minimum required. For example, maybe this pump will require 2 meters of pressure. So minimum 2 meters of the pressure will be required at this point. So and this HV is the vapor pressure of the water. So we need to make sure that the water is not changing into vapor pressure. If we combine all of these figures together, that means that we put the barometric pressure, which is PB, into 10.2, minus the NPSH minus HF, the friction, minus the vapor pressure, and the safety margin. What we usually say the safety margin is, we take 1 or 1.5 meter, because with the change in temperature the vapor pressure will change. So you maybe this system will work good in winters, but in summers it will start having cavitation. Why? Because the vapor pressure changed. To avoid this change in the weather, what we do is we have some safety margin. Now if you can see here, this is negative, this is negative, this is negative, and this is negative. After this calculation, if your result is positive, that means you will not have a cavitation. But if your result is negative, no, you need to change something, you will have a cavitation. How you can do that? Either you need to decrease the NPSH. That means you need to change the pump with low NPSH pump. There are something called low NPSH pumps, where the requirement from 2 will change to 1. So your minus will reduce. That means the chances of positive going to positive will increase. Or you need to change this friction. How you can change the friction? Maybe you have a stainer installed here, remove the stainer. Or maybe you have a valve, throttling valve installed here, remove the throttling valve. Because what throttling valve will be doing? Increasing the resistance in the suction. You don't need to need any suction resistance. Or you can increase the vapor pressure. Can you increase the decrease the vapor pressure? Actually you cannot, because the media which need to the vapor pressure is the characteristic of a media. You cannot change that. So that is something which you cannot change. Safety margin you should always have. So by reducing the friction in the suction or reducing the pump size, you can avoid the cavitation. Another way of reducing the cavitation is actually reducing the speed of the pump. If you remember, when I showed you the NPSH curve, it was like this. So if you reduce the flow or the speed of the pump, the velocity of the water coming inside the pump will also reduce. What this will do? This will reduce the cavitation possibility. So these are the few ways of reducing or eliminating cavitations. Reduce the speed of the pump, reduce the friction inside the pipe, reduce this height, because this height is also very important. You are pumping through, sucking through some long distance. If you are not getting this height, you can if you are not getting this height of suction, you can reduce this. Then you will not have cavitation. So these are the few ways of avoiding the cavitation. So if H is calculated is negative, an inlet pressure of H meters is required, and if H calculated is positive, that means that this much head calculated can the pump can suck the water from. For example, the result of this H is 4 meters. That means you can suck the water from 4 meters with this setup, with this throttling valve, or with this pump, with this NPSH. But if this pump result is only 1 meter, this H is only 1 meter, that means that you cannot have this height more than 1 meter. So if you want to have more than 1 meter, then you need to again reduce the friction, reduce the NPSH, or reduce the speed of the pump. Now, electrical terms, we need motor to run the pump. So whenever we talk about the pumps, whenever I discuss with some people, we always get confused in different types of the powers. In pump, we have 3 major powers. The hydraulic power is the power of the water with some amount of water, with some head, is generated by the pump. This is calculated by rho g QH. Very simple, by flow and head. P2 is the shaft power, the power which is given by the motor through the shaft. P1 is the power taken by the motor through the electricity, through the Saudi Electric Company. So the P1 is the power taken by the pump. P2 is the power taken by the given by the motor to the pump, and PH is the power given or going out from the pump. Now the efficiency of the pump is usually PH over P2. That means this divided by this is the efficiency of the pump. And then the efficiency of the motor is P2 divided by P1. How much kilowatt the motor is giving by taking. For example, this is 5.5 kilowatt motor. When we say 5.5 kilowatt motor, that means the P2 is 5.5 kilowatt. The motor manufacturer is guaranteeing that you can get 5.5 kilowatt out of it. But the P1 is different based on the efficiency of the motor. So the P1 could be 6 kilowatt. Or could be 6.5 kilowatt depending on the efficiency of the motor. So these are all the power, all the efficiencies and the power of the motors. If you want to see which pump is good, always do this: PH divided by P1. Why? This is called line to water efficiency. Why line to water? Because we are taking care of all the efficiencies between the flow end head to the power we take. All the efficiencies comes under it. So this is called the complete efficiency or line to water efficiency of the pump. So whenever you want to see is the motor is good efficiency or the power or the pump is good efficiency, always calculate P1 over PH. P1 you can get from the motor data sheet, PH you can get from the pump data sheet.